Hello everyone, welcome to the YouTube channel Simply Solve. This is Kushan. This is the fourth video of the tutorial series where we were learning derivation of electrostatics. In this video, we are going to learn electric field due to an infinitely long straight wire. Again, if you have any query, do comment in the comment section. Also, subscribe to the channel because more videos are coming. So, let us begin today. So here, this is the uniformly charged straight wire, this wire. So let us consider it has a charge density, rather a linear charge density lambda, right? So this wire has linear charge density. Linear charge density here means that charge per unit length. So it has a linear charge density of lambda, and let us consider any point P anywhere where we need to calculate the electric field due to this charged wire. So before starting off with anything, initially we need to consider a Gaussian surface. So this cylindrical surface that we have drawn over here, this cylindrical surface is the Gaussian surface, and this point P lies on the Gaussian surface that we have drawn. So before we start off, we need to make this thing very clear that this is one of the derivations which shows that shows the application of Gauss's law. So this derivation is actually an application of Gauss's law. So let's begin. So let me call this as surface 1, let me call this as surface 2, S2, and the remaining curved surface, this curved surface area of the cylinder, these are the front face, this is the back face, so these are the two flat faces, circular faces, and this middle portion, the curved face or curved surface, is nothing other than S3, right? Now, so we will calculate flux through each of these faces. So we have electric field here, obviously there will be flux passing through each of these surfaces, this curved surface and these two flat circular surfaces. So let's begin. So first we will calculate flux due to surface 1, and we know from the formula of Gauss's theorem that phi is equal to integration E dot ds, where both S and E are vectors and it is a dot product between them, integration of E dot ds. Again, this is a surface integral and we are calculating for the surface S1. Now, so if I expand this a bit, so it becomes integration surface integral of S1 E ds cos theta, right? Now, see what is the theta or the angle between this electric field and the surface, right? So let us consider here a surface ds. So we need to consider a small component and then we can integrate over the entire region. So this surface, small surface, always, so we know that the area vector is always normal to the surface, right? Thus this area vector is normal to the electric field. Electric field is outwards from this uniformly charged wire, right? So these are normal and there is a 90-degree between them. So therefore we can write it as surface integral S1 E ds cos 90. But we know cos 90 is equal to 0. Therefore this total value becomes 0 since cos 90 is equal to 0, right? So the total flux through this surface S1 is 0, right? Now if we calculate similarly for S2, we will get the same answer 0, right? Like this, due to S2 E dot ds is equal to 0 in the same fashion, just in the way that we have calculated over here, right? Now for the surface 3, right? So surface integral S3 E dot ds, right? Now what happens? So now you see that this electric field is in this direction, and at any point, so for this, if we calculate, for this is, let us consider this is a very small portion of it, and we call it ds over here, right? This is a very small section, and this electric field direction and this small area, its area vector is in the same line, so it is at an angle, so they shares an angle of 0 degree between the electric field and this small surface, right? So it becomes integration E dot ds cos 0 degree, and we know cos 0 degree is 1, so we can write over here as E, we can bring E out of the integration because it is a surface integral and has to be applied over the surface concerned, dot ds cos 0 becomes 1, right? So it becomes E surface integral of S3 ds, right? Now, so we can write it as, so if we integrate this, so the summation of, or rather the integration of the entire small ds pieces turns out to be the surface area of this curved surface of the cylinder, and we know the surface area for the curved surface of the cylinder is nothing other than 2 pi RL, right? 2 pi RL from the concept of geometry. So this is the resultant flux through the surface S3, right? So if we try to calculate the total flux or the net flux, so net flux through the Gaussian surface, so here the Gaussian surface is the entire cylinder, not this circular or this curved surface, so entire one. So net flux through the Gaussian surface right will be phi E, so total flux will be summation of phi due to S1 plus phi due to S2 plus phi due to S3, right? So the first two terms is 0, so we are left with total flux is nothing other than E into 2 pi RL only for the curved surface, right? Got it? Okay. Now we know according, so I can call this my first equation, right? Now according to Gauss's theorem, right, according to Gauss's theorem, we know that this flux through any surface is nothing other than phi is equal to q by epsilon naught, right, where q is the charge enclosed and epsilon naught is the permittivity. Okay. Now here in this case this q is nothing other than lambda into L. So initially I already told that this lambda is nothing other than linear charge density, so charge per unit length. So charge per unit length into this length gives us nothing other than this charge. So I can call this as my, so if I put this value, it becomes phi is equal to lambda L by epsilon naught, and I can call this as my second equation. So it is actually flux F phi E. So from 1 and 2, right, so now I can compare this to equation, right. So from 1 and 2 we get, right, E into 2 pi R L is equal to lambda L by epsilon naught, right, and hence we can equate it as it is like E is equal to lambda. So this L cancel out with this one, and we are left with 1 by 2 pi epsilon naught lambda into r. Or if we write in a bit better way or a common way, we can write it as 1 by 4 pi epsilon naught. We multiply 2 in the numerator as well as in the denominator, 2 lambda by r. So this is the generalized expression. So this is the generalized expression for the electric field due to a uniformly charged wire, right? And the direction is in this direction, right, from any point. So that's all for today. Hope you like this video. So if you have any query, do comment in the comment section. Also subscribe to the channel for more videos. Thank you.